Hello everybody, statistics, and this will be then the last lecture we will do to get some exercises together. But before we start, I want again announce uh, the excursion to the Jade Weserport, which I have organized. And since we are hiring a large coach, we have still some places left, and until the Monday before the excursion you can still participate, and then please just write me an email that you want to participate. And the second one is that next Thursday from 10 to 12 I organized a panel discussion, and it would be really nice if you would join. And it is of course also a statistic topic which we have: de-risking and decoupling in international economic relations, volatile times for investment decisions, and so to speak from two perspectives. One from the real world, represented by Dr. Wolfgang Kornprobst from Siemens in Munich. And he is an economist, so his task is to make the strategic decisions for Siemens, and this, of course, is highly correlated with especially the situation in China. And there you can think of, well, how should I invest, and even how should I invest in Germany? Let's say investing in our wind energy. And most of the goods which I need for a wind energy park right now are coming from China, because they are not only the cheapest in the digital technology, they are also, unfortunately, right now even better than we. But on the other hand, this would be that we will be in energy questions very dependent on China. And for Siemens, it's also a decision: how should we increase directly our China business? Should we still invest in China? With the background that you have there a dictatorship, and maybe they are shutting down in 10 years when a war with Taiwan is starting. And the other one, the other perspective is given by Dr. Jörg Rahn, and he is now for 10, 15 years within the financial business, especially investing large scale, so to speak. He was at Warburg, one of the largest private banks in Germany, for some years. Later on, he was directly in a, so to speak, family office. So he made the decisions of the investments for one of the richest families in Germany, and right now he has its own investment fund, and also works for Tertium family office. So they are not directly working only for one rich family in Germany or Europe, but that they offer their skills for rich persons, rich families. And of course, he is looking every day right now what this golf playing guy in Miami, in Mar-a-Lago, is doing, because if he says something, then of course we know that the stock market will react. So it would be very nice. This will be a hybrid panel discussion, but it would be also nice if I would see somebody of you within here in the lecture hall, but also maybe then hopefully we are 10 people sitting around here, 10, 15 people joining via Zoom, and I try to do this in a digital technical way so that we really can start quite fast a discussion between uh, the two discussions, me, myself, and you, that we are interacting in this panel discussion. Okay, that it was. And then you have also to present, and the presentations, oops, let's take black. The presentations, they will be on, what was it? I think, no, oops. I have a calendar, maybe here. So Tuesday, Wednesday, there it is. Oh no, oops. Except there it is. So it will be then 2021. Tuesday, 20th of May, 20th of May, and Wednesday, 25th, starting from 11. Well, the presentation also from other lectures which I gave, and they had to write a term paper and then presenting. It starts at 10 o'clock, but the first slots I have also already given away. So your slot would be then starting from, or maybe starting from 11 o'clock, and it would be, on the other hand, very nice if you join also before that. So starting at 10, and here we will start from noon, 12 o'clock. So maybe you can directly give me a preference which you have presenting. Tuesday or Wednesday? No preference? Then I will put you just at some time. So roughly, I think it will be 15-20 minutes or something like this. But please, not only for your presentation, but also joining a little bit longer. No preferences? Okay, then I think over the weekend you will get the schedule. Okay, then let's do the last part, that we are doing some exercises in hypothesis testing. Some machine produces boards with a minimum width of 10 millimeters. Boards less than the minimum width cannot be used. The machine has an accuracy of 0.755 millimeters, and this we will use as a proxy of standard deviation. Within a random sample of 100 boards, we have an average width of 9.85 millimeters. And now we want to know, is this just by random? Because we have this volatility here. So we are not surprised that there are some boards which have a length less than 10 millimeters. But given, and now this is really important, an alpha error probability of 10%, is given this alpha of 10% only a random fluctuation where we are not surprised, or is it significant given this alpha equals 10%, and I have to think to, to do some recalibration of my manufacturing machine. My microphone does not work. Oh, sorry. This is not good because here it's working. Test, 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 test. Hello, hello. For the other guy, is it also not working? So then, now it's working because here it says it works. So then it's you have a single, an individual problem. Okay, then I go on. Well, you have to try to fix it by your own. Okay, so this is now the task which we have. Oops, there we are. So what do we have to do? We have n equals 100, larger than 30, so normal distribution. Do I have this normal distribution somewhere here? No, then I just have to open it. There it is. Statistics. Here we are. Table. Normal distribution. A little bit smaller. There. Oops. This is enough. And it was S. And this would be enough. Copy. Let's reduce here also the size. So then we have to formulate our hypothesis. What do we have? H0. This would be mu. Our medium size length is larger or equal than mu0, and this would be our 10 millimeters. And the opposite is H1. Mu is smaller than mu0. And then we know we have to formulate our test statistic. And our test statistic is nothing else than our standardized variable, which follows by assumption because of n equals, oh, sorry, this is example 2 here. Sorry. This, up. Oh, cut and going to example 1 and this one. Here we are. that we calculate from our numbers the test statistic Z, empirical so to speak, which we assume to follow the normal distribution. So we would then have test statistic is Z equals our mu minus mu0 divided by sigma, and we know that the average is scaling with the number of our random sample, so square root by n. So we obtain 9.85 minus 10 divided by 0.75 square root of 100, which is roughly minus 2. So, of course, here with less than, this would mean we have a one-sided test. Because all boards which have a length less than 10 millimeters, this is garbage. So not plus minus, so 10 plus minus, so that the the probability mass of both tails. Let's go back. I think I have the picture still here, hopefully. No, sorry. Ah, here it is. So not this picture, but that we only have here this one-sided test. Okay, and this then would mean normal distribution is symmetrical. We have to look at where the number is roughly 0.1 or the opposite, because the probability mass from minus infinity until here, and this probability mass should be 10%. So the area from here to minus infinity is then 90%. So we have to look up where in my table do I find roughly the number 0.9. And there, let's step in, and then it's roughly this one here. So then we have, so to speak, test our empirical number and compare this with 1.28. So set theo would be 1.28, but of course we have here the left side minus, so compare with minus 1.28. And this would then mean, graphically, we are in this situation. The critical value would be minus 1.28, and our empirical value is minus 2. And so in this case, we have to look, is our empirical value within the rejecting area? So this it would be, and therefore then we can say we have to reject H0. Then H0 has to be rejected, and so to speak, it's for error probability of 0.1, our fluctuation is okay. But if you think of if we would have chosen 5%, then maybe you have already incorporated this number, which we use quite often, then it would be 1.64, or even if you go further, a two-sided 5% would be a one-sided 2.5%, then we would have a critical value of 1.96, which is used very, very often. And then you see decreasing alpha means that at some point we do not reject anymore H0. And then you would say that given this smaller error probability, if this is your level of accuracy, then you have to recalibrate your machine. Okay, next example. Within the distribution of some product, the sellers obtain a fixed income and a provision depending on their revenue. On average, a provision of 600 euro is paid. In the current month, the framework changed due to higher selling prices. So you are acting in some market, and then you see, okay, in general, the selling price has changed in general in my area. And a reason for a higher revenue would be this. Or if you say, well, I cannot sell that much products because all my people are within the next 2 months in holidays during summertime, then I would have a lower revenue. Well, and I now take again a random sample and I look how much have I paid on average. And then I see that I have paid an average a provision of 585 euros with a standard deviation of 80 euros. And now I want to know if this fluctuation is again significant, giving an alpha of 10%. Well, again, I could have copied this because H0 is again the same as we have before, larger than mu0, or H1 mu smaller than mu0, the test statistic. Oh, here I really have to admit, we also have to assume given an n larger than 30. This I have forgotten in this example. Would be then that empirical equals 585 minus 600 over 80. Or no, there is the 100. Sorry, there it is. Square root of 100 is roughly minus 1.875. And again, I have, oops, not like this, but like this. Critical value minus 1.28 minus 1.75. set empirical, set theoretical, see example 1. Uppala. H0 where do I have my table? Again, is not rejected. But, sorry, here, this is the rejecting area, sorry, because here I have written this, has to be rejected, of course. H0 is again rejected. So, it is, so to speak, given this alpha of 10% only a statistical fluctuation. Next one, we want now so to speak, test a medical product, or pharmaceutical product, and the promise of this pharmaceutical product is that it lowers the blood pressure by 20 basis points. And now we make a study, but only with a small number of people. Only N is 9. And there, remember this little guy from the brewery, I think in Scotland or Ireland, which thought about, well, then it is not anymore a good choice to use the normal distribution. Then you have to choose the T distribution. So N smaller than 30. So T distribution. Let's go to our table. And here we have the T distribution. No, that's wrong. This one. Oh, we need only until 9, maybe later on. Oh, let's go to 30. Copy and paste. Let's put it up here. And everything else is, of course, again, the same. Now we have alpha is 1%. Again, one-sided because of why? Well, it lowers. So if it does not lower, so every deviation to a higher blood pressure, this is also rubbish for us. And what we see here is that on average, we obtain a decrease of 21.5. And what we now want to know is, oh, I'm quite happy because only descriptively I have a lowering of more than 20 basis points. Is then really everything okay? Because it could be just by random that I have measured the right people where this pharmaceutical product has worked. It could be if I take a study with 1,000 people that on average the lowering measured lowering effect would be only 18 basis points maybe. And also then I can ask, well, have I chosen the wrong 1,000 people? Is it also given 0.01 for alpha a statistical fluctuation? So then again, now the other way around, H0 mu smaller or equal mu0 and H1 then the opposite. Test statistic is now T from the data, empirical X bar minus mu0, again, volatility measured by standard deviation and square root of number. Putting all these in is 121.5 minus 20 over 1.5 square root of 9. And this is not only roughly, this is directly 3. Well, and this I have to compare with my theoretical, so to speak, theoretical critical value. And where are we? Here we have our 99% confidence level. And remember, we have then to look up not at 9, but it is just a question of definition. That, where is the T statistic? Here. N minus 1 degrees of freedom. This is just a question of how we have defined our numbers in our table. And it is just defined that we take the number of degrees of freedom. So we have to look up in our table not at 9, but at 8. So 8 we have here. So our critical value would be 2.8965. 2.8965. So again, the picture would look like this, that we have our T zero is 2.8965 and T empirical is 3. And again, reject H0. But compared to the other two examples, you see, well, we are quite in the neighborhood. And if you have chosen maybe alpha 0.1%, then of course your theoretical value would be on the right of your. And actually, the anecdote I told you that there was some guy in a bachelor colloquium who just said, well, alpha is always 5% and this is bullshit. I'm sorry. Alpha is not always 5%. You have to choose a relevant alpha because of your question you are posing. Well, quite often an alpha of 5% is reasonable. But always you have to think what is a reasonable choice of alpha. No matter that in, let's say, 9 out of 10 experiments, alpha equals 5 is a good choice. So it is not because everybody is choosing 5%, then I do not think about the question, what is the right alpha level? Okay, and of course you have to be careful that you then do not manipulate yourself by, well, I'm setting just the alpha in that way that I'm just rejecting because you want to reject H0. This is also not doing good statistics. Okay, next example. Now I think we are comparing two averages. Here at first we just compared averages, and now we are comparing two averages with each other. Let's say we have an insurance company and a telephone hotline. The phone calls are evaluated via some new software. This, I think, if you are in some hotline, then at first you also have to answer. Is it okay that we are recording your talk with the, how is it called? Operator. Yeah. Without having the software, the phone calls during 1 month had a connecting time average of 22 minutes within 1,500 calls. With the software, connecting time was only 18 minutes out of 1,200 calls. The unbiased estimation of the standard deviations are given by 15 and 12. Remember, unbiased means divided by n minus 1. And now, well, if we reduce the connection time, then of course the operator can do on average per day more clients than before. And this would be, of course, nice for the insurance company. Then their investment using this new software would, so to speak, increase their output. So then we have, so to speak, a positive effect. Investing in software means more output. This is what we want to have. Well, we see descriptively again, the connecting time is reduced, but now we want to know, well, is it maybe only a statistical fluctuation? And in general, we have nothing by implementing this software package. And so now we choose this general, quite often chosen level of alpha equals 5%. Then let's go into what we have to calculate. And this is very similar to the test statistics which we have already calculated. So the first one is just we putting in the differences of these two averages, because testing on the same number, this would be then 0. And we have to insert now an aggregated fluctuation measured by standard deviation, and this is, so to speak, the Gaussian sum of the two, or even Pythagorean sum of these two deviations which we have given. So this again, A, B, C, and this is then more or less A squared plus B squared square root is C from Pythagoras. Okay, so then maybe, can I cut this? No, sorry. Anyway, where are we? Here we are. So first, again, at 2000, 1200, 1500, of course, we can use the standard deviation. Then we take this one. And now, of course, H0 would be nothing has changed. And H1 would be we have a change. And of course, again, it is formulated in that way that hopefully we can reject H0, that it has changed, that we have a significant reduction given an alpha of 5%. Test statistic is then set, since we have the normal distribution, is then x bar 1 minus x bar 2 over sigma x1, x2, and this sigma hat we have to calculate by square root of sigma 1 hat squared over n1 plus sigma 2 hat squared over n2, which is then given by here. 15 and this one, and this one. So 15 squared over plus 12 squared over 1200. This, of course, we can then 15 over 100. 100 square root is then 1 over 10 times 15 plus 12. And if I calculated this is roughly 0.52. Square root of 27, this is even good. Square root of 27 is 3 square root of 3 divided by 3. This is roughly 1.7. 0.3 times 1.7, yeah, this is quite good. Roughly, it is a little bit more than 0.5 if you do the calculation in your head. So we obtain then 22 minus 18 over 0.52 is roughly 7.7, and our two-sided 5% is our famous 1.96. So that TO is 1.96. Picture. I always say having this picture in behind your head, this would be quite good, because then you know, well, I'm of course within the tail. H0 rejected. And then you can say, well, given alpha equals 5%, was a good investment into the software. So two are left. I think this we will make here. The next one, quite easy, is just more or less the same, testing on averages. Now testing just on a part, and test the hypothesis that party A, well, the new government has been implemented just in Germany. Our last polls we had in just some month ago. The hypothesis that party A has obtained more than 50% of the votes for alpha equals 1% with a random sample of 400. In the random of 400 people, 204, so more descriptively than 50%, has said, well, we will vote for party 8. And now again, we won't say, well, do I get significantly given alpha equals 1% really more than 50% because of my survey? So again, normal distribution, 400 people. And now we could just insert in the average formula, but since this is quite often done for the proportion, then we can directly choose this formula here. So actually this descriptive probability minus pi 0 divided by n. There you see then you again obtain this multiplying by n because you are dividing by 1 over square root. This probability is divided by n and then n is coming up. Okay, so again, h0, what do we have? We say now we want to reject the h0 in case. So we formulated that pi is smaller than pi 0, our 50%, because this is what we are testing against. No problem, everything is recorded and you can look it up later. Pi 0, upsa, and then just inserting, we have our set empirical is, at first I calculate this one. So this would be then 0.5 times n minus 0.5 divided by n is our 400. So we obtain 0.025. And then inserting all this, 204 over 400 minus 0.5 divided by 0.025. This fortunately is just 0.51, and in the end we obtain 0.4, 0.1. Where do we have 0.1? This would be then roughly here. We need 0.99. So Z theoretical is 2.33. And unfortunately, we have that TO is 2.33 and Z empirical is 0.4 f of x, x. So we are on the left and H0 is not rejected. So because of our survey, we cannot say, well, although descriptively it is more than 50%, given a level of accuracy, given an error probability of 1% means, well, then I have to admit it's just a statistical fluctuation. If you ask the next 400 people, please do not be surprised when the outcome is only 48%. And the last one. And this is our nice little chi-square test. Oops. There I gave you already the numbers. Due to the time, I think we will also do this. Remember, in the beginning of the lecture, we have already calculated this table. I will give you just how you calculate these tables for the empirical and the theoretical numbers. So now what we have, again, an insurance company wants to increase the number of sold household insurances and is planning a market activity. And they say, well, I do not want to call everybody. I want to choose the right people. And it is assumed that, so to speak, risk-averse people which already have a life insurance, there the probability would be also quite high that they want to buy another product if I call them an household insurance. And then I can look in my data. Well, people found I find in already in my data people who have already both insurances. Then I find also people who have only one of these insurances, and I find within my portfolio people who have until now no insurance, not a household and not a life insurance. And these are the numbers here. So overall, I think, chosen that it is, let's see, can I just do this quite fast? Well, maybe it is even enough time. What do we have? We have 436, 511, 121, and 481. N, oops, N, H, N, oops, N, live, and live. So overall, I have here 947, and here I have this plus this. Well, then let's just do it. And overall, I have this plus this as overall numbers. Well, and what we now want to do is, from my data, can I say, are my two people, are these two, not people, two insurances depend on each other or not? And I see what I unfortunately have forgotten. One very important number I have forgotten. Hopefully you see what I have forgotten in my exercise. When I now want to test, are these two variables, life insurance and household insurance, depend on each other? What is missing in my exercise? Well, my error probability is missing with, and let's assume alpha again equals 10%. This I really forgot. I always said, well, you have to think about alpha, and now I forgot it by myself. Well, and then, of course, we can calculate our empirical probabilities. Oh, sorry, just only the numbers. Because then this would be our 436 divided by the overall number. This would be empirical. And also this numbers, this, I think, this I can do, oops, by choosing this down here, this down here, and hopefully, yeah, this should also work. And this should be then 100, or, oh no, I haven't chosen this, so let's skip, yeah, sorry, here, okay, so we are back in, and then not E11 but E6 should it be. H E11 changed with E6. It's the same number, but then I can because why? Oh, $11 H. Though I only need this one, and with $6. Good. Now we have it, and now I can put it down, and I have the 100%. And this would be also nice because this 100% here, then you have a clue that your calculation was hopefully right. And let's put this in percent. So this would be then our empirical, and the theoretical would be then, of course, copy. Up. When we now multiply equals this probability from this border times this one, and this one times this one, and equals this one times this one, and equals this one times, oops, equals this one times this one. So, and again, percent. And what you now see is, of course, that this number differs from this number. And in the starting point of the lecture, we said, well, this is at least a descriptive clue that our two variables are not are depending on each other. But now we take in an error probability of alpha equals 10%. You see here, these are the same numbers which I directly calculate. Can I now say, well, it's just a random fluctuation, or given this error probability, can I reject the null hypothesis? And this is then our chi-square testing. Then, of course, we have to calculate this quite complicated statistical test statistic, but with a software package, just insert the numbers. So then let's formulate at first our hypotheses. So H0, household and life household are independent, H1 household and life are not independent. Chi-square empirical, then you have to insert all these numbers, and we have also to think about our degrees of freedom. Well, and there, of course, we have, of course, to admit this is quite easy because this is K is 2 and L is 2, because we have here just a two-dimensional problem, and overall we have only 1 degree of freedom. So then, no, oops, and sorry, this was the wrong slide. Cut this and moving to this one. Zip. Here we are. I think I just also copy my monster here. This one. Zip. No. Yeah, there we are. And this is our test statistic. And t, oops, t equals k minus 1 times L minus 1 is 2 minus 1 times 2 minus 1. It's 1 degree of freedom. Well, this is due to that you have a very simple example here. And inserting all these numbers, then you will obtain roughly, where is it, 107. Well, if you have only 1 degree of freedom, you should not be very surprised that you obtain very large numbers. But we need also from our table, from this chi-squared distribution, t, 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 there it is. Uh, and 10%. So cut was again this one here. Yep. Since we have only 1 degree of freedom. This one. Then of course 10%, 1 degree of freedom, chi-squared theoretical would be 2.7. And remember, for n equals 1, it has not this distribution, but it looked like just a decreasing function. But anyway, we have the 107 here, and we have our 2.7 here, theoretical chi-squared and empirical chi-squared. So we are in this part reject H0. They are not depending on each other. Well, if you have only 1 degree of freedom doing a chi-squared test, this you can of course question, but I have done this here in my example in order that I do not have to calculate that much numbers to obtain the numbers which I have to feed in the chi-squared. I haven't already looked up in your term papers. Have you, by accident, the topic of chi-square testing? I don't know. No. Okay. Anyway, so you have seen it, and well, this chi-square test on independence. This if you want to make a survey in your bachelor thesis or so, this is actually very easy to do if you have 10 questions and then you just want to look, well, do they depend on each other? Is it a good choice to interpret them only separately? So this is a good choice if you have 10 questions that you in the end do for all together simultaneously a chi-square test, because then maybe you see by the answers you have posed 10 questions, but 3 of them are highly interconnected with the other ones, so that you, so to speak, can skip 3 out of your 10 answers. And this would be then really nice if you do something like this in your bachelor thesis and not only doing descriptive analysis. Because from only descriptive analysis, in the end, as I said here today, it could be the case that you are interpreting some result as, whoa, it's more than 50% in my survey. But doing this hypothesis testing would mean, well, I obtained more than 50%, but it's only a statistical fluctuation given alpha equals 5%. And this is really, really important, because otherwise you would do decisions on wrong assumptions. Okay, so that it was, and then I will give you the schedule for your presentation, and then we will see within the next 2 weeks, and hopefully you will join the panel discussion. Thank you very much for today.